Welcome along. In this first learning outcome, we're going to explore why numerical methods exist at all and how they let us tackle problems that ordinary algebra simply can't crack. So why do we reach for numerical methods in the first place? The honest truth is that many equations can't be solved neatly with algebra. Take x cubed minus x minus 1 equals 0. There's no tidy formula that hands you the answer. What a numerical method does instead is grind out a good approximation using arithmetic that a calculator or computer can repeat in an instant, as accurate as you need it to be. Across engineering, finance, science, and statistics, that's often the only practical way through. In this unit, the two big jobs are finding roots, that is solving equations, and finding areas under curves. Most of what follows shares the same simple rhythm, so it's worth seeing it laid out. You start with a sensible first estimate, often by sketching a graph or spotting where the function changes sign. Then you apply a rule that turns your current guess into a better one, and you feed each new answer straight back in, building a sequence x0, x1, x2, and so on. Finally, you stop once successive values agree to the number of decimal places you're after, and that's your answer. Let's fix a few words you'll hear again and again. Iteration just means repeating a process, using each result as the input for the next step. An iterative formula is a rule of the form x sub n plus 1 equals g of x sub n, which generates the next estimate from the current one. Convergence is when the sequence settles towards a single fixed value, your answer, while divergence is the opposite, when the estimates drift apart and never settle, and the method fails. Let's look a little closer at what an iterating function actually does. It applies the same rule over and over. You put in x0 and get out x1, put in x1 and get out x2, and on it goes, building a whole sequence of numbers. If that sequence converges, its limit L satisfies L equals g of L, and we call that a fixed point, a value the function leaves unchanged. The word iterate comes from the Latin for to repeat, and the real power is that one simple rule, repeated, closes in on the answer. Let's see it in action by estimating the square root of 2. Our rule is x sub n plus 1 equals a half times x sub n plus 2 over x sub n, and we'll start from x0 equals 1. First step, a half of 1 plus 2 over 1 is a half of 3, which is 1.5. Feed that back in, and a half of 1.5 plus 2 over 1.5 gives about 1.416667, and one more turn brings us to 1.414216. By the next step, it's settled at 1.414214, which is the square root of 2 to 6 decimal places. Look how quickly one repeated rule gets there. Here's a completely different way to trap a root. A root of f of x equals 0 is simply where the graph crosses the x-axis. Now, if f is continuous and its values at 2 points, a and b, have opposite signs, then a root has to lie somewhere between them, because a continuous curve can't get from below the axis to above it without passing through 0. From there, you narrow the interval, either by a decimal search or by bisection, which just means repeated halving, until the root is pinned down as tightly as you need. Let's picture that with f of x equals x cubed minus x minus 1. At x equals 1, we get 1 minus 1 minus 1, which is minus 1, so the curve is below the axis there. At x equals 2, we get 8 minus 2 minus 1, which is plus 5, comfortably above the axis. The sign has flipped between 1 and 2, so a root must live in that interval, and the true value turns out to be about 1.325. Now let's actually hunt that root down to 2 decimal places by watching the sign of f of x. We know it's between 1 and 2, so we close in. F of 1.3 comes out at about minus 0.103, still negative, while f of 1.4 is plus 0.344, so the root is now between 1.3 and 1.4. Squeeze again, f of 1.32 is minus 0.02, and f of 1.33 is plus 0.023, trapping it between those two, and f of 1.325 tips just positive at plus 0.01. So to 2 decimal places, the root is 1.32, or more precisely 1.3247. It's a lovely method, but it isn't foolproof, so let's be clear about when to trust it. It works well when the function is continuous, there's exactly one root in your interval, and the curve crosses the axis cleanly. It lets you down when there's a repeated root, where the curve merely touches the axis, and the signs match on both sides, or when 2 roots sit in the same interval, and their sign changes cancel out and get missed. And watch for discontinuities, something like 1 over x minus 2 flips sign across its asymptote, where there's actually no root at all, so always sketch the function first. Let's bring iteration back and make it more general. The trick is to rearrange f of x equals 0 into the form x equals g of x, and then iterate with x sub n plus 1 equals g of x sub n. For x cubed minus x minus 1 equals 0, we can write x cubed equals x plus 1 and take the cube root, so g of x is the cube root of x plus 1. Here's the subtle part though, the same equation can be rearranged several ways, and some converge while others diverge. It only settles near the root when the gradient, the size of g dash of x, is less than 1 there. There's a neat way to see whether an iteration will behave. Plot y equals g of x and the straight line y equals x on the same axis, and the root sits exactly where the 2 graphs cross, since that's where x equals g of x. As you iterate, you draw a staircase up to the curve, across to the line, and repeat. Because those steps close in on the crossing point, the sequence converges to the root, which, for our example, is about 1.325. Let's work this fixed point iteration all the way through, using x sub n plus 1 equals the cube root of x sub n plus 1, starting from x naught equals 1. The first step is the cube root of 2, about 1.259921. Feed that back, and the cube root of 2.25921 gives 1.31294, then 1.322354, then 1.324269. Carry on, and the values creep to 1.324633, then 1.324703, settling at 1.3247 to 4 decimal places. Notice how each step shrinks smaller than the last. That's convergence you can actually watch happening. Now for the fastest method in the toolkit, Newton-Raphson, which cleverly uses the gradient of the curve. The formula is x sub n plus 1 equals x sub n minus f of x sub n divided by f dash of x sub n. Picture drawing the tangent to the curve at your current estimate. Wherever that tangent meets the x-axis is your next, much better estimate. It usually converges astonishingly fast, roughly doubling the number of correct digits each step, though it does need the derivative f dash of x, and it can stumble if that derivative is 0, or your starting point is poor. Let's picture Newton-Raphson working on f of x equals x cubed minus x minus 1. Start at x naught equals 1.5, sitting on the curve, and draw the tangent there. That tangent cuts the x-axis at about 1.348, already closer to the true root. Repeat from that point, and the estimates rush in towards 1.3247, each tangent giving a far better guess than the one before. Let's put numbers on that. With f of x equals x cubed minus x minus 1, the derivative f dash of x is 3x squared minus 1, and we start from x naught equals 1.5. Now f of 1.5 is 0.875, and f dash of 1.5 is 5.75, so x1 is 1.5 minus 0.875 over 5.75, which gives 1.347826. Repeat, and x2 comes to 1.325157, and one more step lands on 1.324718, already correct to 6 decimal places. That's far fewer steps than fixed point iteration needed, which is exactly why Newton-Raphson is so widely used. Let's switch from finding roots to finding areas. Definite integration is really about the area under a curve between two limits, but some functions have no integration formula at all, so we estimate that area numerically instead. The idea is to slice the region into thin vertical strips of equal width h, estimate each strip's area, and add them all up. The trapezium rule gives each strip a straight top, while Simpson's rule fits curved, parabolic tops for extra accuracy, and generally the more strips you use, the smaller the width and the closer your estimate gets. Take the trapezium rule first. Each strip is approximated by a trapezium that joins the tops of neighbouring ordinates, and an ordinate is just the height of the curve at each x. The formula is h/2 times the first height plus the last height plus twice the sum of all the ones in between. So the two n's, y0 and yn, are each counted once, and every value in the middle gets doubled. Because the tops are straight, the estimate is slightly off wherever the curve bends. Let's estimate the integral of 1 over x from 1 to 2 using 4 strips, so h is 0.25, and the true answer is the natural log of 2, about 0.693147. Our x values 1, 1.25, 1.5, 1.75, and 2 give heights of 1, 0 to 8, 0.571429, and 0.5. The two ends add to 1.5, and the three middle heights sum to about 2.038096. So the area is 0.25 over 2 times 1.5 plus twice 2.38096. That's the 125 times 5.576192, giving 0 known source 97024, close to the true value, and just a touch too big because 1 over x curves upwards. Simpson's rule is a real step up in accuracy. Instead of straight tops, it fits a parabola through each pair of strips, so it hugs the curve much more closely. The formula is h/3 times the first plus the last height, plus 4 times the odd-numbered heights, plus 2 times the inside even-numbered ones. It needs an even number of strips, an odd number of ordinates, and for the same number of strips, it's usually far more accurate than the trapezium rule. Let's redo that same integral with Simpson's rule and the very same heights. The two ends, y0 and y4, still add to 1.5. The odd ones, y1 plus y3, come to 1.371429, and the single inside even one, y2, is 0.6667. So the area is 25 over 3 times 1.5 plus 4 times 1.371429 plus 2 times 0.67, which works out as 0.33 times 83948, giving 4. Compare that with the true y 3 plus 7, it's dramatically closer than the trapezium rules, 4. Since every estimate carries some error, we need sensible ways to measure it. The absolute error is just the size of the difference, the approximate value minus the true value, ignoring the sign, and it's in the same units as the quantity. The relative error takes that and divides it by the size of the true value, giving a ratio, and multiplying by 100 turns it into a percentage error. Why does the distinction matter? Because a 1 centimetre error is trivial on a road, but enormous on a microchip, and it's the relative error that puts things in context. Let's measure how good our two integration estimates really were against the true value 0.693147. The trapezium estimate was 0.697024, so its absolute error is the difference 0.3877, and dividing by the true value gives a relative error of 0.594, that's about 0.599%. The Simpson estimate was 0.693254, with an absolute error of just 0.07, a relative error of 0.34, or about 0.94%. So Simpson's rule is roughly 36 times more accurate here. Its percentage error is tiny by comparison. In practice, you'd rarely grind through all this by hand, and a spreadsheet is perfect for it. For iteration, you put x0 in a cell, write the iterative formula in the cell below, then fill down, and the whole sequence appears in seconds. For integration, you list the x values and heights in columns, and combine them with sum or sum product using the trapezium or Simpson weights. Scientific and graphing calculators have built-in solvers and integration functions too, And tools like Desmos and GeoGebra let you see routes, sign changes and areas, which helps you pick a good starting value. The point is that IT removes the arithmetic drudgery, so you can focus on method, accuracy and checking. Let me show you what those formulas actually look like in a spreadsheet. For fixed point iteration, you'd type the cube root of A1 plus 1, referencing the cell above, and fill down. For a Newton-Raphson step on our cubic, you'd write A1 minus, the bracket A1 cubed, minus A1 minus 1, over 3 times A1 squared minus 1. To list the heights, you just enter 1 over B1 for each x in column B, and then the trapezium and Simpson totals are simply weighted sums. H over 2 times, first plus last plus twice the middle, or H over 3 times, first plus last plus 4 times the odds, plus 2 times the evens. Type the pattern once, fill it down, and the machine does the rest. Let's pull the whole outcome together. Numerical methods give us good approximate answers when an exact analytic solution is impossible or impractical. An iterating function repeats a rule, x sub n plus 1 equals g of x sub n, to build a sequence that can converge to a root, a fixed point. Roots can also be located by a change of sign, as long as you watch for repeated roots, hidden double roots, and discontinuities. And we met 2 ways to refine roots: fixed point iteration and the faster Newton-Raphson, plus the trapezium and Simpson's rules for areas, with absolute and relative error to check our accuracy, all of it made easy by IT tools. So that completes our first look at why numerical methods matter and how the main techniques work, from iteration and change of sign through to Newton-Raphson, the trapezium rule and Simpson's rule. To take this further, the reading list points you to solid classics like Stroud and Booth's Engineering Mathematics and Bird's Higher Engineering Mathematics, alongside journal articles on teaching these methods. Do make use of the interactive tools as well. Desmos and GeoGebra are brilliant for watching iterations and areas come to life. And the MEI Integral Maths site has plenty on numerical methods. There are worked case studies out there too, such as estimating distance from a velocity time table, which show these ideas solving genuinely real problems. Everything you need sits on the Moodle for this unit, so do explore it before you tackle the assignment.